I'm happy to present our paper on optimal dynamic allocation, simplicity through information design, which is joint work with Itai, Ashlagi, and Afshin Nikzad. So there are many examples of non-monetary markets where agents strategically wait to be assigned to an object, like markets for public housing and organ allocation. And these markets typically use some form of waiting lists, which are not necessarily optimally designed. So a common problem that we see in practice is inefficiency, which arises because of high waiting times. So to give you some examples, we know from available statistics that millions of families are currently waiting in public housing waiting lists. And similarly, in kidney allocation, which also happens dynamically over time, we also see that the wait time for a person's first kidney transplant can be extremely long. And at the same time, the discard rate of kidneys is currently more than 20%. So motivated by these issues, in this paper, we formalize the problem and study the optimal allocation in large markets with multiple objects and agent types. And in our model, agents have private types, quasi-linear payoffs in their waiting cost, and supermodular utilities. So if a planner wants to design the system now optimally with a goal to maximize social welfare, we ask who waits how long and gets what in the welfare maximizing solution. And after we characterize the optimal mechanism, we ask how can we now implement this optimal mechanism in a simple way. So different versions of these questions have already been studied in the literature, but in more restricted settings than ours. So most of the papers find optimal solutions within a special class of mechanisms, like, for example, they may sometimes consider a fixed queuing system or consider only two types. And related questions and optimal mechanisms of similar structure have also appeared in money-burning and costly signaling settings, like in papers by Condorelli and Hardliner of Garden. But in contrast to these works, in this paper, we instead optimize over a general class of steady-state mechanisms in this large market setting. We also relax the assumption on separable utilities and study a more general class of supermodular utilities. We also consider multiple types of both agents and objects. And finally, we explore the connection between optimal mechanisms and information design. Okay, so hopefully the motivation was clear. So next I want to introduce you to the details of our setup. And then I will talk about a motivating example, our formal findings and proofs, and finally an extension for discrete markets. So let's jump right into the model. We study a continuum model of agents who arrive at the flow rate 1 and objects which arrive at the flow rate smaller than 1. So essentially our market is over-demanded, but I just want to make clear that this assumption is not really restrictive for our results. And then each agent has a private type theta, which is drawn IID from a continuous distribution. And on the other side of the market, we have objects with discrete types omega. So there are n types of objects plus what we call a null object, which is actually in infinite supply and has no real value. So we will just use this for technical simplicity to assign agents who don't get a real object. And each agent has a utility U that depends on their type theta. And also when the agent faces a lottery over objects, it will also depend on the expected object type omega bar that they get. So we make two technical assumptions about U. First, that U is supermodular, which is necessary and sufficient for incentive compatibility by Roche's characterization. And also that the first derivative of U is convex in its second argument, and this is needed for optimization regions I will explain later. So of course, a simple example of a utility function that satisfies both of these properties is the separable utility, which is the standard in mechanism design anyways. So each agent also has a waiting cost, which is increasing in time. So their total payoff is simply their utility minus their waiting cost. And in total, the planner maximizes the social welfare, which is defined as the average of all agents' payoffs. And by the revelation principle, we can focus only on direct revelation mechanisms that take this agent's reported type theta and then assign them what we call an allocation plan, which is essentially a joint probability distribution over the times of allocation and object types. But we will be looking at steady state mechanisms within this class, which also need to be incentive compatible and individually rational. So we can now rephrase our main question and ask which mechanism with these properties will have the highest social welfare. So let's get an idea of how the optimal mechanism might look like through an example. So suppose we are in a simple setting where agent types are drawn from the uniform distribution. Agents have separable utilities, and there are also two object types, the low type omega-1, the blue objects, and the high type omega-2, and each of them have capacity 0.25. So a natural solution here is to consider one Q for each object. So the yellow omega-2 objects can go to the top Q, Q2, and the blue objects can go to the second Q, Q1. So naturally, the agents with the highest types, so in the dark green part you see here, will join Q2, and then because like the system seems to be at the steady state, their arriving mass needs to be equal to the capacity 0.25 of the yellow objects. And the second highest group here will join Q1 and get the blue objects now. And finally, we have the bottom half of the agents who get the null weight at all. So this solution is essentially an implementation of the positive assortative matching rule. And it would indeed be optimal if there are no weighting costs. But here, incentive compatibility imposes that both this dark green and light green group of agents must pay in waiting time to actually get an object. So let's now see whether we can do better than this positive assortative solution. So instead of one Q per object, we will use some pooling. And specifically, a fraction 1 minus epsilon of its object type will be sent to the same Q as we had before. But now the other fraction epsilon will be sent to the opposite Q. And by solving the system, we can find that the social welfare is actually a function of this pooling parameter epsilon and takes its maximum at exactly 1/2. And as a result, this means that full pooling, so when epsilon equals 1/2, achieves higher welfare than any other value of epsilon. So in this case, the two Qs we had before are replaced by one Q that allocates yellow and blue objects uniformly at random. So this example already tells us that even for two objects, assortative mechanisms are not always optimal. So the optimal mechanism is the one that best trade-offs losses from its allocation and gains from reduced weighting costs. So it becomes clear that some form of pooling will be needed, but the question is really how much pooling. So it turns out that the optimal mechanism often uses some pooling and actually takes the form of what we call a monotone disjoint queue mechanism. So this is essentially a system of disjoint queues where each queue pulls only adjacent object types. For example, in this figure, the yellow omega-2 objects are pulled together with the adjacent red and blue objects in the second highest queue. But this pooling is only possible for consecutive object types. So instead, if we had a scenario where these red objects are also pulled with the blue omega-1 objects in a different queue, this would not be possible in this class of mechanism. So in a monotone disjoint queue mechanism, each agent will choose the queue that gives her the highest payoff and wait there until she gets an object. And our first result shows that the optimal mechanism is a monotone disjoint queue mechanism. But the previous mechanism has two constraints. First, that once an agent gets assigned an object, she can't decline it. And the second is that the mechanism uses potentially multiple queues. But in practice, like in organ allocation, agents can often decline offers, and the system usually uses only one queue. So in our second result, we ask whether allowing for these declines and using only a single queue comes at the social welfare loss. And the answer to this question is actually no, when the planner can use information design. So in this case, what will happen is that the planner will use a single first come first served queue for everyone. So when an object here arrives, the planner will see the object's type and then draw a signal from her optimally designed information disclosure policy, and then reveal the signal to the agent. So since this policy mu is common knowledge, the agent knows what type of object the signal might mean, and so what they might expect. So they can decide whether they want to wait longer or accept the object and leave. So the optimal information disclosure policy has, again, a similar pooling structure. And formally, our theorem states that the optimal mechanism can be implemented by a first come first served policy with declines paired with an information disclosure policy that pulls adjacent object types. So moving now to the proof details of these results, we found that classic ironing techniques that are commonly used to show optimality of pooling are not directly applicable in our framework, either because our utilities are supermodular or because of the existence of capacity constraints and multiple object types. So instead, we take a different approach here. So we characterize the extreme points of a function space defined by a majorization property that I will explain. And then we show that the optimal mechanism is indeed an extreme point of the space. So what we do more specifically, the first step is to write an incentive compatible steady mechanism in a reduced form. So this reduced form describes the expected object type and expected waiting cost for each agent type theta as two functions. And then using a very classic Myerson type of technique, we can eliminate the waiting cost and simply write the social welfare maximization problem in terms of a function phi. So we call this function the virtual payo function. And this function depends both on the agent type theta and the allocation rule x theta. And the third step is to understand the set S of feasible allocation rules that we are optimizing over. So it is quite easy to show that this set can actually be described in terms of a weak majorization property. So we show that S is exactly the set of increasing rules that are weakly majorized by the positive assortative matching rule XP. And I don't really want to get in details about this majorization definition, but I just want to say that the high level, its strong form describes some type of like stochastic dominance property. And its weak form allows just like for some discards of objects. So given these observations, we can now see that our optimization problem gets a much nicer convex form. So first, our objective itself is convex, and this is because of our assumption on the derivative of u. But also, using again results from this majorization theory, we can show that the set of allocation rules S is also convex, which is nice because it allows us to apply the Barre's maximum principle and reduce our search for the optimal mechanism just to the extreme points of the set S. And on top of that, we are lucky because by this recent paper by Kleiner, Moldovano, and Strack, we know that each extreme point of S has a very simple structure. So its allocation rule is identical to the positive assortative matching XP that you see here in the graph, except for a countable set of intervals. So like a set like this blue region here. And outside of these intervals, its extreme point and as a result, the optimal rule itself will be identical to the positive assortative rule XP. But now within this blue region, it will be equal to the average value of XP. So this is actually nice because it means that if we want to implement the solution, each such interval will correspond to exactly one queue in a monotone disjoint queue mechanism. Okay, so like this was the proof and the large market model. So it's natural to ask whether our results change in a discrete market setting. So through additional theory and simulations, we studied this question in a market with Poisson arrivals, lambda and lambda n, and linear weighting costs. So now see that the model allows us for some fluctuations, so the allocation must depend on the state of the pool. And in this model, we show again that the social welfare under a mechanism that simulates the optimal monotone disjoint queue mechanism that I described in the continuum model. Now this mechanism indeed approaches the second best as the lambda parameter goes to infinity. And the same similar result holds for the first come first served result. The proof in both cases actually relies on a concentration bound that we verify through simulations. And through simulations, we also verify that our results hold for small markets as well, and that convergence is fast. And before moving to the conclusion, I would like to mention that there is more related work on matching, information design in markets, and costly signaling, as you see on the slide. And finally, as a conclusion, I would like to reiterate our paper's main message. So we characterize the optimal mechanism and show that it can be implemented in two ways. First, through a system of at most 2n plus 1 disjoint queues with pooling of adjacent object types. And second, through a single first come first served queue with declines when the planner can design the information he discloses to agents. Thank you.